Okay, everybody, and welcome to the next webinar in the Thieme Cheminar series. Today we'll be talking about soluble graphene nanoarchitectures. My name is Dr. Charlotte Marshall, and I am a senior publisher in chemistry, and I manage 2 journals as part of our journals portfolio. And it's a pleasure to be with you today. We have a fantastic lineup of speakers for you, and our session today is hosted and chaired by Professor so we thank everybody for being a part of this session today. Before we get started, we have a few notices to make just about today's Cheminar so that you're fully aware. So this Cheminar will be available shortly after today's session. As such, we will be keeping our audience on mute during the webinar, but we do encourage you to ask as many questions as possible via our Q&A webinar. And our aim is to ask these questions live after each presentation, so there should be around 10 minutes for a Q&A via that Q&A window after each presentation. We would very much welcome your thoughts of what you're thinking of the case. So if you'd like to tweet us at Thieme Chemistry and use the hashtag Cheminar, we'd love to hear from you. And if you'd like to find out more information about our Cheminar series, as well as the products offered by Thieme Chemistry, there are a couple of links to subscribe to our newsletters, and I believe these will also be available after the session as well. So I'll be talking to you for about 5 minutes, just about Thieme, to give you a bit of an overview of what we do, about a couple of journals that I manage here at Thieme Chemistry, before handing over to our chair for today. So Thieme, if you're not aware, is a German company with an international presence and over 130 years of experience in publishing science. Thieme Chemistry itself specializes mostly in organic synthesis, helping chemists acquire knowledge about organic chemistry, as well as helping them devise efficient synthetic strategies. So you may well be aware of some of our synthesis, Synlet, Synfax, Synopen, as well as science of synthesis, SOS, and pharmaceutical substances. 2 of the newer journals within our portfolio are Organic Materials and Circularity Now. And these are the 2 journals that I manage, and they are the journals that I'm going to be talking to you about briefly right now. So Sustainability and Circularity Now is the newest journal in our portfolio, free to publish, fully open access. And the real aim of this journal is to tackle the most serious challenges within sustainability. The idea of helping to shape an ambitious and genuinely interdisciplinary agenda of the global crises that we face in humanity and as a planet. The idea is for the journal to facilitate scholarly, public, and policy conversation across the globe to help us work together to resolve these global crises. The journal is quite unique in that it is the first of our now series of journals, which we will be expanding shortly. But it is quite unique in that it's one of the only journals to actually put the UN Sustainable Development Goals on themselves. We have logos that we put on the papers that have been approved by the UN for our exclusive use. And so what it means is authors are able to identify more relevant papers more quickly, but also your funders can see how you're aligning with the Sustainable Development Goals, and we understand that's something quite important to our community. The journal also offers a different kind of review from the traditional peer review. So we have the option as well, but we also offer, which is select crowd review, and a number of Thieme Chemistry journals offer this as an option. This is a really interesting initiative, which involves a group or a crowd of reviewers looking at your paper, not just 1 or 2 reviewer reports. The idea that they have anonymous discussion about your paper through a safe portal for a limited period of time, with the idea that you will get the most you will get more feedback about your paper, so we'll improve it so it's the best it can be. Also, it means that you'll get a quicker turnaround of reviewer comments as well. So there's more information about the journal on the link there, and you can connect with us via our social media links below. Today's session seminar is really about organic materials, and we have a journal called Organic Materials within our portfolio. This journal covers a wide range of topics within organic materials. So you're looking at porous materials, liquid crystals, polymers, you name it. If it's organic materials based, it's welcome in our journal. We also offer a type of article called a practical review, which is really meant to be a primer for people just joining a particular topic, overview of what key aspects they need to know about that particular topic. And it's an article type that's quite unique to our journal. We are delighted to say that we have been recently indexed in Scopus, and we now have a site score of 3.6 with, and we also have further indexing and abstracting in other areas such as the DOAJ as well. And again, the journal link is available at the bottom should you wish to have any more information. Finally, I'd like to just point out our Best Papers Awards initiative. This has been going for some time on our journal Synthesis and SynLet, and we have just launched our inaugural Best Papers Award for SynOpen and Organic Materials this year. And this journal offers to the highest impact original research that we publish in the journal. And this is decided by the editorial and advisory board by looking at all of the papers from the previous year that qualify and deciding which meets the criteria the best. Will receive a prize money and a certificate. And as I've mentioned, the prize winners are selected based on the previous year. And I'm delighted to say that we have our winner, our inaugural winner for organic materials, Professor Ikai, speaking as part of this webinar today. Thank you so much for joining us. It's a pleasure to have you on board with this Cheminar. So now I would like to hand over to our chair, Professor Narita, and I'd like to just say a few words about him as an introduction. So Professor Narita was born and raised in Yokohama. He received his bachelor's and master's degree in chemistry at the University of Tokyo under the supervision of Professor Nakamura. He then joined Max Planck Institute for Polymer Research in Mainz, Germany, and obtained his doctorate in chemistry from Johannes University of Mainz in 2014. In the same year, he became a project leader in the synthetic chemistry department at the MPIP. And in 2018, he joined OIST as an assistant professor to lead the organic and carbon nanomaterials unit. And he's now working full-time as an assistant professor at OIST since 2020. And he is also an associate editor for Organic Materials, the journal that I've just presented. So I need to hand over to Professor Narita. So over to you.
Thank you very much, Ali, for the kind introduction. And can you see the slideshow now?
Yep, see them perfectly. Thank you.
I'm very happy and honored to chair this web Cheminar team about soluble graphene nanoarchitectures. So already I got introduced, but briefly, let me show the map that I was in Tokyo at the University of Tokyo. And then 2010, I moved to Germany, where I actually stayed 10 years. And in 2008, I got adjunct position and started to get prepared. I was waiting for this building constructed and opened. And 2020, I moved to Okinawa, where I'm now doing my research. And I live here in Okinawa Island. Actually, this is, in a way, the center of East Asia, somewhere between Japan, and it's close to Seoul and also China and Southeast Asian countries. So if you are interested, please let me know, and I'm very happy to host you here. And as my current group, Organic and Carbon Materials Unit at OIST, and I'd like to acknowledge them first, and I also want to, of course, appreciate Professor Klaus Müller, and I spent with him for 10 years in Mainz, and a lot of learning and guidance, and I'm here thanks to him. And I also want to acknowledge all the group members and these, so we didn't have a chance to get nice picture recently due to the COVID pandemic, but these are more recent. Yeah, I also appreciate funding. And so I'd like to introduce my research related to also to the topic of today's web Cheminar. And so it is already quite well known as fascinating 2D materials for a lot of applications. I'm not going to list the properties and applications, but want to mention that it is a drawback actually that there's no band gap. If we want graphene for semiconductors, for example, as field effect transistors or for optical applications where we want to absorb or emit light. If we make the nanostructures of graphene, which are typically nanographenes, we have open energy gap, band gap, or Holm-Lummer gap through the quantum confinement effect, and we can have a variety of interesting optical, electronic, and magnetic properties solely depending on structures. And these are two typical types of nanographene structure. One is graphene nanoribbons, quasi one-dimensional, and another one is often called graphene quantum dots or graphene fragments. And in chemistry, we call them nanographs, but all of these can be considered as extended polycyclic aromatic hydrocarbons. And these are 2D graphene nanostructures, nanographenes, but we will see that these go beyond the planar to 3D, including the 3D structure, which we try to call graphene nanoarchitecture together. Not only nanographenes, but we are more inclusive than nanographenes for going for graphene nanoarchitectures. And nanoribbons sounds like nanocarbon materials, but actually it's belong to the polymer chemistry. So this is a very simplistic theoretical slide, but if we pi extend polyacetylene, we get the polyparaphenylene. If we get so-called angular polyacenes, but this is considered already as N equal 4. So the armchair graphene nanoribbons with the 4 carbon atoms in the middle. And then further polyylene or polyperinaphthalene in a classical term is 5-AGNL. So these are polymers, and actually other polymers, but other included in the graphene nanoarchitectures. So during my PhD in Professor Klaus Müller's group, I worked on other polymerization of such monomer to get the graphene nanoribbons, which are substituted with alkyl chains, and this becomes soluble. So the former graphene nanoribbons in early 2000s were often insoluble and difficult to characterize or apply, but by making them soluble, we can visualize and also deposit them for further device fabrications and so on. So I'd like to introduce one of the last works Professor Klaus Müller in the synthesis of graphene nanoribbons, and so Dr. Xuelin Yao, who was PhD student, and he became postdoc at Oxford and now professor at Chunyan University. He achieved the synthesis of 8 AGNLs, demonstrated the fascinating absorption property. So going to the 2,400 nanometers, and this corresponds to the optical band gap of around 0.5 electron volt. And we demonstrated collaborating with MPIP, very high intrinsic charge carrier mobility of these graphene nanoribbons by using ultra-fast threshold photoconductivity measurements. And going to the nanographene quantum dots, so Professor Müller has demonstrated the very facile and quantitative synthesis of hexabenzocoronin HBC using hexafluorobenzene as precursor, and then doing the cyclochrome. But this HBC, when it's not substituted, completely insoluble, but more 2013, to Dr. Yuanzi Tang, who was postdoc, and Professor Xinliang Fen, working together with Professor Muller, demonstrated that it is possible to chlorinate the edges of such HPC and other larger nanographene to make perchlorinated variants of nanographene, and they all become soluble. And you can see option or color of solution all solubilized by having such large structures. And this becomes a very example of soluble graphene nanoarchitectures. And more recently, Professor Jishan Wu reported together with Professor Diaz Garcia that these such zigzag-edged nanographenes have very interesting emission properties, and this can actually apply to the lasing devices. In my group, a bit related, but we developed a graphene nanostructure, which can be called dibenzo HIST ovaline, and we call this DBOB. I'm working together with Professor Giuseppe Patelno and Professor Scotogonella, together with also Professor Lanzani, that this shows stimulated emission by transient absorption. So it's very emissive, red emissive nanographene with sharp absorption emission with high contact yield. And we can also demonstrate amplified spontaneous emission and lasing. And we are using graphene for various applications. Based on this strong emission, we achieved the lasing together with Diaz Garcia, and we made photodetector with Professor Affronte in combination with graphene. Oyster has many neuroscientists, and I collaborated with Professor Marco Terenzio recently to apply such nanographene for bioimaging. And in super resolution, also working together with Dr. Xiaoming Liu and Dr. Sami Chabon at MPIP, and we could demonstrate our nanographene and neuron together in the cover, and we demonstrate really high resolution fluorescent images of neuron development of peptides in the structure. And with Professor Thomas Bachet, University of Mainz, we also demonstrate that this can be used for single photon emission. And further, we worked postdoc Yofeng Fu, now in Central South University of China, and then my postdoc could synthesize such large 3D helical graphene nanostructure and demonstrating near-infrared emission. And Dr. Hao Wu works JJQ, who is now back in China in the Chinese University of Hong Kong in Chinese campus. We put such a pi-extended helicene or non-helical nanographene and radical to make the combination of nanographene, electricity, and magnetic properties. And such works I'm working on. I'd like to move on to the introduction of our focus issue. So we had a great opportunity to organize the issue on the soluble graphene nanoarchitectures, firstly initiated by the chief editor of Organic Materials, Professor Michael Marcellets. And we also had worked on with Professor Shofei Wan as guest editor from the Department of Chemistry, Tsinghua University, China. And we aim to showcase the recent developments on the synthesis and characterization application of such soluble graphene nanoarchitecture, covering, of course, nanography molecules and nanoribbons, and also pi-extended helicines, cycloarenes, nanobelts, and so on and so on. And we had great contributions. I'm showing some representatives, for example, contribution by Yuanzi Tang's group, showing the quadrupole 5 helicene units with nice structures and also contribution by Professor Chunyan showing the nanobenzenoid 3 nanographene containing 5, 6, 7, 8 members. And we also had contribution from Professor Jima and Professor Sillian in collaboration with Roman Fazer, trying to make such interesting tetrabenzylene structure in solution and then visualized on surface actually, but it's still soluble. And we had also nice review by Professor Shandong Do about the progress of polycyclic boron-doped carbons. And from today's speaker, Professor Ikai, we had also very nice contribution about trypsin-based one-handed helical ladder polymer, showing the interdisciplinary type of materials, hybridizing graphene nanoarchitectures and ladder type helical conjugated helical polymers. And as Charlie mentioned, his co-authors got the Organic Materials Best Paper Award for 2023, and I'd like to congratulate on him for this great achievement, and thank you for the presentation is Cheminar and also great contribution to our focus issue. And we also had excellent contribution from another speaker of today's Cheminar, Professor Uwe Bunz, about the limit of phosphotips from pentacene to octacene. And I think he will also introduce this work in his talk, but I invite all of you to read his paper and also other contributions in our focus issue and also other paper in the organelles. And very importantly, I'd like to advertise that we are still accepting late submissions to our focus issue. And if you wanted to have your work added to this great collections of in organic materials, please feel free to let me know or submit by mentioning that you are interested in the consideration for this focus issue. Of course, there is a very high quality of peer review. Actually, the peer review is also great, and I'm very much looking forward to your potential contributions. And I'd like to thank your kind attention and to move on to the So I'd like to invite our first speaker, Professor Uwe Bunz, to share his screen.
Can you hear me?
Yes. So I think now you
Can
can.
you see me? Okay, now I can.
So I'd like to.
Can you see my presentation?
Yes. And I think I now see your slides and.
Good. Yeah.
You could share, please.
Good. Can I start?
So please let me first introduce you, and then you. So Professor Uwe Bunz is from the Institute of Organic Chemistry, University of Heidelberg. So he was born in Houston, now called Arnsberg, and he studied in Munich chemistry at the Ludwig Maximilian University, where he received his diploma in chemistry in 1987. The doctorate in chemistry, Dr. Leonard, in 1990. And he did a postdoctoral stay in the group of Professor Peter Holhart in UC Berkeley. And then he joined NPIP for his habilitation, I think, as a Liebig scholar. And he got his habilitation in 1997 from Johannes Gutenberg University of Mainz, which is next to NPIP Max Planck Institute. And they moved to the University of South California as associate professor.
South Carolina.
South Carolina. And he got promoted to full professor there in 2001. In 2003, Georgia Tech, and then in 2010, he became W3 professor. So coming back to Germany, and since 2010, he is at the Ruprecht-Karls University, Heidelberg, the Organic Chemistry Institute, one of the organic chemistry chairs, I think. So he has received different prizes, awards, including Carrier Award of NSF and Camille Dreyfus Award and Best Faculty Paper from Georgia Institute of Technology. And he has published more than 500 papers and cited more than 25,000 times. So talk today is entitled Stabilization Acids and Other Acids. So Professor Bunz, please start when you're ready.
Thank you, Aki, for the nice words of introduction. Yeah, let me start. I'm a person I like to first do the acknowledgements first. I would like to thank Jan Freudenberg, Kai Seehafer, Frank Rominger, and some other people here who are my collaborators, in which this chemistry would have never been possible. I would like to first introduce for everybody what are acenes and what are azacenes and what are they good for. So acenes are basically linearly annulated benzene rings, and they come in different sizes, from anthracene, the smallest ones, then tetracene, pentacene, hexacene, heptacene, in blue, nonacene, and they all decrease in stability and solubility, and increase in reactivity. So nonacene is an interesting case, as it is so you can actually isolate it in substance, which is fairly unusual as a parent. Heteroacenes are acenes where you have, instead of a CH group, a pyridinic organ, which help to stabilize these materials considerably. If we go into the history here of particularly of the heteroacenes, they are actually older than the acenes. And Hinsberg was the first person who actually described tetracenes in great detail and very well. Later, then, this research was not until in 1967, Kummer and Zimmermann actually were able to show that azapentacenes can be synthesized by oxidation of the corresponding H compounds, which form typically by a condensation of dihydroxy to diamino, aromatic dihydroxy to aromatic. And then the next big step forward was done basically 2001 by John Anthony, when he introduced the TIPS ethynyl groups, which are now, I think, regarded as best stabilizing groups, basically that are used to stabilize acenes, arenes, and so on. Our own contributions started in 2008 or 2009, and we introduced tetraaza pentacene, number 40 here, and this turned out to be actually a really good semiconductor, as was shown by Chen Miao. Our later development since 2010 basically used palladium catalyst to actually build up the corresponding azacenes. And one thing you can see is that you always obtain NH compounds, which then later have to be oxidized. So compounds are, of course, anti-aromatic, but they are actually more stable than the corresponding aromatic pentascenes or hexacenes or higher acenes. The first thing I want to show you is our foray into higher acenes with 4 TIPS ethynyl groups. So here we basically take dibromo anthracene, make the arine and react it with furan. And then in the second reaction, basically we create here in the second Diels-Alder reaction, we create ions which we then react with TIPS ethynyl lithium, and then of course reduce with SnCl2 into the corresponding acenes. And the stabilities here decrease dramatically. So the hexacene is, interestingly enough, the most stable compound here, followed by the heptacene, while the octacene then here is basically not very stable. And if you want to go to non-acenes, 4 alkynyl groups are not enough anymore, but you actually have Nicole Saiter. You have to use actually 6 ethynyl groups, and you use basically here this intermediate, which is with which you do a double Diels-Alder reaction here, deoxygenation, and then, as usual, alkylation, and here the tin dichloride reduction. And you can get the out here in 16 to 63% yield, depending upon substitution. One of the things we found very interesting is that the most stable one here is the one where you have alkoxy groups here in positions, which was sort of like unexpected. However, their half-lives are not particularly long. So the longest one has a half-life of 9 hours. Here you can see the absorption spectra. They all center around 1000 nanometers. Now, what happens if you introduce actually nitrogen into this? Then you stabilize actually these species considerably. And our first foray here into the synthesis of stable azoheptacenes was to just to species here under palladium catalysis, Buchwald-Hartwig. And you can do this in a way that you can either get 1 or 2 benzene unity between the alkynyl groups, build up then the number of different azacenes here fairly easily using standard technology like palladium catalysis and oxidation. What we can see is here, if we look at the stability, the most stable of all heptacenes here is this diheptacene, which has like a stability of larger than 14 days. It can also be processed into a thin film transistor with a moderate electron mobility here. If you then are nitrogens, or if you actually pull the TIPS ethynyl groups apart, then your stability decreases. Now, if you complete the nitrogens, then your stability also decreases dramatically. theoretically here, and you can see the corresponding heptazine here has a half-life of 25 hours. We have done some store works here, and yes, these things work as transistors, but they are not particularly impressive. One of the things that was of importance to us was to find different modes of stabilizing azacenes or azenes at all. And one of the things we discovered that we actually could form sigma dimers here by taking just this corresponding this dihydro compound here, treated with manganese dioxide either in chloroform here, and then you basically get 4% of the corresponding dimer, or you can do this in THF, and then basically you don't find any butterfly dimers here anymore, but basically only here the corresponding cross-shaped desired dimer here. And you can see these dimers here are, the cross-shaped dimers are very, very stable here, and basically they are over days in solution stable. The reason for that is, of course, they are packaged very, very nicely in TIPS ethynyl groups, as you can see here on the right-hand side, from the rotating molecules. What's the mechanism of this dimerization reaction? So we assume that in the presence of manganese dioxide, which you always need, or you could also use lead dioxide, that you form a highly stabilized radical, which basically is stabilized by these two imines here. And that this radical here then can not only dimerize, that's the thing I've shown you, but it can also react with radical traps fairly easily. And so what you can get is the corresponding arrow or amino substituted or the corresponding thio substituted heptazines here. And in all cases here, or in most cases here, you obtain them as an H compound. If you now try, for example, to oxidize the corresponding amine further, you will actually just wind up with a corresponding ketone. However, in the case of the ether, you can use lead dioxide, and you can actually get the corresponding true heptazine out here, or a tetraisoheptazine. Good. The second part of my talk will concern itself with dimer indenofluorides. So Akimitsu has, of course, done some really nice work on this, and we basically have done the same thing, but just with heterocyclic adding nitrogens. One thing, so you see here the synthetic scheme. One thing you can really see is that again here we got over this stabilized intermediate radical here, and we get out basically an H compound that, using DDQ and heat, gives you the corresponding radical here. And what was interesting was that a small detail to note here is that you have to use trichlorophanyl groups to stabilize this material here. Regular mesotyl groups would not do the job in the sense that they would actually form decomposition products here. So this material here is stable over, and then of course slowly decomposes. Good. So one of the things we also I want to talk to is our addiction to TIPS ethynyl. So everybody uses them, and but there is an alternative, and that's the use of bulky phenylene groups here. So one of the things we have done is we have tried to add a biphenyl to pentacene-dione, but the corresponding adduct here is not particularly stable with a half-life of 7. So it's like phenyl groups offer similar protection as some bridges. However, if you repeat the same experiment here with a pentacene, you actually, even though you have more protecting groups, your stability will be even less, and you get immediate photooxidation here, so that there is a half-life of less than 5 minutes here. However, this can be circumvented if you actually close the bridge between the aryl groups. And what you do is, in your product here, you have, of course, in your first product here, you have chlorine groups here, and you can just perform a Yamamoto coupling, and they smoothly go and give the corresponding doubly bridged here in 23% yield. And you can see here a crystal structure that the material is completely protected from air and anything else. We try to measure stability, and after 14 days or so, the material in air and ambient conditions was still completely stable. So this time is at least, this material is 100 times more stable than for example, this TIPS pentacene, which has a half-life here of 3 hours. And this, interestingly enough, is the fact that it's easier oxidized than this TIPS acetylene. So than TIPS pen, yet it's less reactive. And also do this game a little bit differently. Instead of putting the chlorine atoms in the para position, you can put them into the meta position here. And you also form a very nicely bridged, doubly bridged. But in that case here, your is now twisted, which is interesting for chiroptical and similar. So this twist here is 49 degrees. And in the other case, it's only like 10 or 16 degrees. Good. So that's one of the areas we, of course, want to explore further. Now, the last topic here, we have made some compounds in which spontaneously, and in this case here, this dimerization must occur over diuretical species here, and to our surprise, we found here this corresponding cage, which has a lengthened carbon-carbon single bond length, despite that this is between sp2 and sp3 center here. Good. You can see the crystal structure here. When you stir it up, you can actually monomerize these things again, and then they polymerize. So the reason for this, if you have the sulfurs either in the southern or the northern position here, you have completely different radical properties. In one case, you have a para-quinodimethyl-dimethane species here, which is stable, and so you basically have a very, very small radical character here. And on the other hand, in the lower system, you have an auto-quinodimethyl structure here, where you have basically a fully conjugated system, and you have like a stabilization here of the radical species here with the yeah, as I said, you can break up the cage here, and you can observe all these things here, of course, by EPR spectra, and so on and so on. IR, and so all these things all go together. What's perhaps the most remarkable thing is here that during formation, there is a head to tail dimer that forms actually with more or less 25 kilocal per mole enthalpy here. Of course, can only dimerize in the way it does. However, if you heat the stuff up in substance, then of course this pre-organization is lost, and you just get normal polymerization. Good. The last surprise I want to share is that we had a really unusual solid state rearrangement here. We wanted to make actually tetrahexahexene, but when we crystallized the material here, we got basically out a biscarbodiamide. And but when we redissolve the stuff again, dichromethane here, we got the azacene back. So in collaboration with Andreas Droyf, we did some calculations, and what turns out is that the crystal packing itself actually basically forces this type of arrangement, which is very unusual. I mean, the explanation for this is that of course we have very large pi surfaces, and these large pi surfaces exert very large dispersion forces, attractive or also as van der Waals forces non-attractive, and basically the ideal packing here seems to be the biscarbodiamide, which is unusual because normally molecules can always evade molecular rearrangement crystallizing, but here in this case it seems not to be possible. With this, I think I'm finished, and I would like to thank you for your attention, and of course I'm open for questions.
Thank you very much, Professor Bunz, Uwe, for the great talk. And so, as announced, if you have questions, please write in the chat, and I will select out the questions. So there's already one question or two questions from Dr. Soichiro Nakatsuka. And first question or comment is, thank you for interesting talk. So in the stability of other acenes, are other acenes decomposed to something or react with something?
So acenes basically, when they decompose, they decompose at the non-aza rings, and they typically do to photooxidation as normal azenes do. So in that way, they are very similar to normal azenes. Does that answer your question?
So I'm not so I
understand his question correctly.
Wait for that. I think yes, but I think if Dr. Nakatsuka can type in the chat the additional question that I can still read. So, please let me meanwhile read another next question. So Professor Chunyan has asked Professor Bunz, their radicals are very interesting. Can you observe their thermochromic and mechanochromic? Thanks.
Yeah, we have not looked at their mechanochromic behavior, but we should look at them. And the other one was what? Mechanochromic, and the first one was?
So thermochromic.
Okay, yeah. So the thermochromic behavior we can see when we take, for example, the dimer and then heat it up. Then we see a color change, and then we form the diradical again. That we can see.
Yeah, and thank you. And another question from Dr. Professor Omoyuki Ikai. Thank you very much for your great. I think the shielded azene would be chiral. Have the resolution and the chiroptical properties of the shielded azene been investigated?
Yes, we actually can separate the bridge by chiral HPLC, and we are collaborating with Michael Masterlatz at the moment to get larger amounts of the corresponding enantiomers and look at their properties and so on, packing properties, which I think will be very, very exciting.
Thank you. And so there is another question from Dr. Soichiro Nakatsuka, which is in denofluorine derivative, some products of iodocyclization of propargyl alcohols can be applicable for divergent synthesis for its derivatives. Have you ever tried?
No, but I think you are right. Yes, they should be. No, but we haven't tried. So one thing we have of course tried is instead of the trichlorphenyl groups, we use what Professor Narita uses, the mesotyl groups. But strangely enough, these heterocyclic diradicals seem to be more reactive than the pure hydrocarbons. And so we find four-membered ring formation by CH insertion and stuff like that. So it's like a little bit different.
So related to that case, let me ask one question, but that's a really great work. So I'm interested in the diradical properties. So have you checked the variable temperature EPL, for example, a square?
Yes, we have done all of these, and what you have is basically, if I remember correctly, a singlet ground, a singlet ground state, an open shell singlet ground state with a very, very small barrier to triplet. Triplet. And of course, that makes absolute sense because the radical centers are perpendicular to each other, so they want to be singlet grounds, open shell singlets, or do they want to be triplets? So this is one of the ways how you can actually engineer. And I think Akimitsu, you have done this, shown this beautifully. You can actually decrease singlet triplet open shell gaps.
So it's still similar on that molecule. Yes. So other is correcting too much that properly observed for.
No. It just the azenes just make it more reactive. But otherwise, I think it's pretty much the same as the same properties as itself, which it would be actually surprising if they would not.
Yes. So how about the stability? Because we had a big problem with the stability. Maybe
So
it's more.
we have, on the one hand side, we have the trichloro groups, and they increase stability dramatically. But you can also use these enthral groups that have the butyl phenols attached in the right position, and then get even more stable.
And can you measure the squid in solid state?
Yeah, with the chloros we can, but strangely enough, with the more stable enthral ones, we have had problems, and we don't know why. But the trichloros, yes, and we get reasonable results out that are exactly what you would expect. We have like maybe 1 or 2% of monoradical and a little bit of non-radical dirt, but 95% or more are actually the diradical. With the enthral groups, which should be much better, squid is much more difficult, and we don't know why.
Okay. Thank you very much. So audience, so we can have some more questions. So if you please feel free to write your questions in the chat, and I will read it out. So meanwhile, let me ask one last case. In the previous slide, it was really surprising and interesting that it's opening up in the
Yes.
production.
We were shocked.
Have you tried if you can thermally induce this ring opening in other way?
I mean, so what we find is, so the more bulky the substituents here are, the more it goes into this direction here. So of course our fundamental goal is, can we push that it's also stable in the soluble or solute state? And calculations suggest that if you add lots of electron accepting groups, then you might actually get as the only form that you get the bis carbon diamide.
And can you guess from it's different between solution and crystalline state, but also electronic properties, how do they like?
Electronic properties are dramatically different. I mean, the azine has a typical azine absorption, and the crystalline state, the stuff is basically colorless because bis carbon diamides are just lousy conjugating units. No?
Wow, very interesting.
Yeah. No, so and I think this is
color.
The one of the first examples where one observes it.
Yes, yeah, that's really fantastic new switching system.
Yeah, but we don't. So we have this system for more than a year, or actually 2 years, but we don't know the exact mechanism by which it works. That's we are hesitant to publish.
I see. Yeah. It's, this looks really like of high potential and really new.
Yes. Thank you.
Yeah, but thank you for your wonderful talk again. I think there is no more question. It was really clear, and I'd like to thank you again for the great talk.
Thank you for the invitation.
Thank you very much also for joining this webcam, and I was very happy that you could make it. Thank you very much. So please let us move to the next speaker, Professor. I think it is so next. So Professor Tomoyuki Ikai, and please. So Professor Bunz, could you stop sharing the screen and? Professor Bunz, could you stop sharing the screen? And thank you very much. And Professor Ikai, could you start to screen share?
Okay.
Yes, now we see background. Yes, so please let me introduce Professor Tomoyuki Ikai from Nagoya University. So he studied at Nagoya University, receiving his Bachelor of Science and PhD degrees, working in the group of Professor Yoshio Okamoto and Professor Masami Kamigaito. And in 2008, he became an assistant professor at Nagoya University. And he also visited the Massachusetts Institute of Technology in the same year as visiting assistant professor, working in the group of Professor Timothy Swaggart. Then he moved to Kanagawa University in 2009 and got promoted to an associate professor. So he moved to Kanagawa University in 2009 and then got promoted to associate professor in 2014. He joined again Professor Swaggart's group at MIT in 2016, staying there up to 2017 as visiting associate professor, and then moved to Nagoya University as an associate professor in 2019. And so this year he got full professor, and congratulations for the promotion. And so his research interested in the design and synthesis of chiral functional molecules and polymers and supramolecules with unique structures, and especially ladder polymers representing graphene nano architectures in this web Cheminar. And he also got different awards, including encouragement of research in polymer science from the Society of Polymer Science Japan in 2016, Japan Association for Chemical Innovation Award for Young Researchers in 2020, and MC Asia 2022 Poster Award, the synthesis of single-handed helical conjugated ladder polymers. And the title of his talk today is Control of Secondary Structure in Designed Ladder Polymers. So Professor Ikai, if you're ready, please start your presentation.
Thank you for the introduction, Narita sensei. So I'm Tomo Ikai from Nagoya University. First of all, I'd like to thank Professor Narita for the very kind invitation to the wonderful online Thieme Cheminar's soluble graphene nano architecture. I'm enjoying this special opportunity. Thank you so much. And so I'm going to start my talk now. So before I get into the main topic, explain the background of my recent interest in the control of the secondary structure in the designed ladder polymers. The variety of synthetic polymer have been developed and applied to the job application, but I believe that there is still a lot of potential in the polymer development. So this can be clear when we look at the biological system. So the biochemical molecules, such as the protein, have the precise primary structure and can form the specific secondary structure. And their intramolecular assembly result in the tertiary structure, which are further intramolecular form the quaternary structure. And due to such the unique higher order structure, the DNA and the protein show the sophisticated functions such as the genetic information, the highly selective catalyst, and the mass transport and molecular motor and energy conversion. And compared to this biological example, the functional level of the synthetic polymer is still considered to be quite low. We think so this difference between the synthetic and the biological system is most likely due to the presence or absence of higher order structures. Most of the synthetic polymer don't have the specific conformation but exist as a random coil structure. So this structural randomness is probably due the main reason for the lack of the advanced functionality in the synthetic polymers. Of course, the variety of synthetic polymer with secondary structure have been reported, and these structures were produced by using the steric effect and intramolecular interaction between the pendant. But these structures have been constructed based on a lot of trial and error, and it's really difficult to predict whether the polymer chain will form the secondary structure or not before synthesis. It's even more challenging to control the structural details such as the helical pitch, diameter, and cavity size, and helical handedness. So we can say that the design and well-defined secondary structure is still a big challenge in the field of the polymer chemistry. So here I show the achievement roadmap of higher order structure. So we can say that the synthetic polymer have made big progress in the control of the primary structure, but they are still far behind biomacromolecules with a quaternary structure. So to achieve the advanced functional system, so we need to figure out how to control the secondary structure of the synthetic polymer. So recently, we proposed the new strategy for construction of the secondary structure in a traditional way. So let me explain it using the Lego blocks. So not many kids play in this way, but if you connect these Lego blocks at only a single point, the structure cannot be clearly because the connection becomes a moving part. So this situation is very similar to the linear polymer connected by the single chemical bond. So the linear polymer basically have the random coil conformation due to the around the bond axis. And on the other hand, when the Lego blocks are connected at 2 points, the structure can be uniformly defined due to no moving part. So for the polymer design, and if the monomer unit could be connected by the more than 2 chemical bond, so it would be much easier to construct the desired secondary structure. It's not so well known, but such polymer exists, so-called radar polymers. The radar polymers are defined as macromolecules consisting of cyclic repeating unit linked by 2 or more chemical bonds. Right, the radar polymer have a shape of radar at the molecular level. And I'd like to emphasize that each repeating unit of the radar polymer cannot freely rotate around the bond axis. So due to this feature, have the thermal and mechanical stability and structural designability not found in the conventional linear polymers. So for the various useful approach for the synthesis of radar are being reported, but most of these approaches simply produce these coplanar achiral radar polymers. On the other hand, the biological system makes a clever stereogenic center chirality to form the 3-dimensional secondary structure. So combining this insight, so we recently came up with this idea that we realized the 3D geometry control of synthetic polymer by incorporating the chirality into the design of radar polymer. So this is the same logic that if we connect chiral and achiral Lego blocks at 2 points alternatively, so it will always form the specific structure. So to prove this idea, so I collaborated with Swagger at MIT. So previously, the Swagger reported alkene benz annulation reaction that is a useful reaction to produce a fully pi conjugated radar polymer through the molecular cyclization of the precursor polymer. Here, so we replace one of the A chiral monomer with a chiral monomer to construct the secondary structure. So we designed this polymer containing the chiral trypsin unit in the main chain and carried out the alkene benzonylation. And based on the various analysis, so we conclude that this precursor polymer are completely converted into the radar polymer in a quantitative and chemoselective manner. And so now, so we are further pushing this concept of the control of the polymer geometry through radarization. So today, so I will introduce some recent study. The first one is about the synthesis of the spiral conjugated helical radar polymer. And chiral spiral frame, no conformational freedom, would also be a good candidate for the chiral Lego blocks to construct a molecular level helical structure. So we first that this alkene benzonylation could be applied to the pi extension of the spiral by Indian framework through this model reaction. In contrast to the previous study using the trypsin unit, so in this case, the cyclization product showed a complicated NMR. So this suggests the undesired product formation occurred. So we component and found that this byproduct RAD-B was also produced along with the expected compound RAD-A based on the NMR analysis. And we byproduct formation mechanism in this paper. And so we believe that this byproduct RAD-B was produced through this complicated multi-step rearrangement process. And the key point is that the alkene benzonylation occurred after rearrangement of this allele group from the 6 to the 5 position of the indent rings. So this caused the formation of the byproduct. So this result indicates that if this alkene benzonylation was applied to the polymer synthesis, so this kind of the irregular radar polymer with two types of repeating unit would be produced. So the well-defined construction of the secondary structure, so it's necessary to completely suppress this side reaction. So to address this issue, so we the reaction condition and substrate structure. And it takes about 2 years, but we finally found that this methyl groups introduced at the 2 and 6 position of the alkoxyphenyl pendant significantly activity of this reaction. And this perfectly suppress the side reaction, so probably due to the electron donating ability and the selective effect of the group. This cyclization products show the very simple NMR, even without purification, and all of the resonance peak could be a expected compound. And we also confirmed the formation of this compound by the crystal X-ray analysis. So we then apply this modified alkene benzonylation to the synthesis of the spiral conjugated helical radar polymers. So to this end, so we design and synthesize this precursor polymer containing the chiral spiral unit by the Suzuki coupling conformalization of these two monomers. And wooden polymer was then treated with this acid to transform the random coil precursor one-handed helical rubber polymers. And after the reaction, so that this CC triple bond in poly A were completely consumed as confirmed by the IR analysis. And the obtained rubber polymer, the simple NMR, similar to the model reaction, and only 4 resonance peaks were observed in the aromatic region as expected from the structure. And so this spectral analysis suggested the one-handed spiral conjugate helical rubber polymer was successfully produced through the modified alkene benzonulations. So here is a possible secondary structure optimized by the calculation. So we can see the ribbon-shaped rigid left-handed helical structure without a helical cavity. And we then investigate the optical property of these rubber polymers and obtain the left and right-handed helical rubber polymers show these mirror image circular dichroism and circularly polarized lumen, in contrast to the precursor polymer showing almost no CD and CPL signal. So these chiroptical signal of rubber polymer are clearly derived from the helical secondary. Okay, so and due to the time limitation, so I cannot go into detail here, but we have also synthesized this the tubular helix with a pi electron-rich helical. So we found that this polymer showed a good chiral recognition for the variety of chiral aromatic compound with point, axial, and planar chirality. And so we believe that this pi electron-rich hydrophobic helical cavity play a key role for the efficient enantioseparation, and so probably one of the enantiomer would be favorably encapsulated within this hydrophobic cavity in a direct manner through the attractive pi and hydrophobic interaction. Okay, so I move to the next topic. Okay, so the helical rubber polymer are the binary rubber polymer composed of the chiral C unit and bisphenylphenylene B unit. So to change the secondary structure, so we need to replace the chiral unit. There are not so many options for the chiral unit available for the rubber polymer synthesis. So therefore, in this project, so we investigate whether it would be possible to modulate the secondary structure of the same chiral unit. So to achieve this, so we designed this CBAB type rubber polymer containing the A chiral spacer A unit as a third component in addition to the unit. So we try to synthesize this pi extended helical rubber polymer with trypsin as a chiral unit and naphthalene, fluorine, and unit as a chiral spacer. And we investigate the impact of the A chiral spacer unit on the secondary structure. And so we first check the modified alkylation of the naphthalene and fluorine and carbazole molecule proceeded quantitatively in all cases. So we could easily synthesize these AB type rubber polymers. The structures looks complicated, but proton NMR of the rubber polymer is very simple, as shown here. And calculation, so we found that this naphthalene-based rubber polymer from the right-handed helical structure are the same as the previous study, but the helical pitch is expanded to the 8 nanometer, about 4 times larger than the previous one. So this poly 2NA has a loosely coiled helical structure. On the other hand, this fluorine and carbazole-based rubber polymer different secondary structure from the naphthalene type in terms of the helical geometry and helical handedness. So these polymers possess the left-handed extended without helical cavity. Such a difference in the secondary structure are also reflected in the circular dichroism. The reversal of the CD intensity CD between the naphthalene type and other polymers is likely due to the opposite macromolecular helicity. And we also confirmed that this helical ladder showed almost no solvent temperature dependence in the CD signal. So this indicates that this pi extended helical ladder structure is highly stable. So we believe that this ladder polymer contribute to the future developed robust functional chiral material whose performance is independent of the external environment. Okay, so I will sum up this project. So here, so we demonstrated the handedness and helical geometry of this polymer can be modulated by incorporating the simple achiral spacer unit into the polymer backbone as a third monomer component. It's a great honor to receive the Best Paper Award for this study. Thank you very much. Okay, so using the remaining time, so I'll talk about the last topic. Okay, so far, so I explained we can construct the secondary structure through the lateralization of the precursor polymer containing the unit. And as you can expect, that if we don't use a chiral unit, that this kind of the zigzag-shaped coplanar is produced. So based on this situation, so this project aimed at the synthesis of the helical ladder polymer from the only simple achiral monomer, so without using any chiral element. So for containing the new achiral methylphenylene unit with a C2V symmetry. So in this design, so if the alkene benzonylation proceeds, each repeating unit would be forced into the helical arrangement. So this would result in the fully pi conjugated ladder polymer with a spiral geometry. So the resulting polymer no chiral element. So the polymer would exist as a racemic state containing an equal mixture of the right and left-handed helical structure. So we investigate the resolution of helix using chiral HPLC. And so far, the several examples of the fully conjugated helical ladder polymer have been reported by Morin and Du, but all of this exercise as racemic mixture. So there are no report of optically active fully pi conjugate helical ladder polymers. So we synthesized this polymer, precursor polymer, with an average molar mass of 50,000, which was corresponding to the degree of polymerization of about 50. After lateralization, we got this ladder polymer showing the broad but reasonable proton NMR spectrum. And here we show the absorption and photoluminescence spectra of the polymer and the model compound before and after lateralization. And so this random coil present by blue line gave the relatively broad and featureless absorption and PL spectrum. On the other hand, the LADA polymer showed a relatively sharp and well-resolved spectra due to the vibration structure derived from the rigid LADA backbone. So this spectral difference between the precursor and LADA polymers is in good agreement with those of the model compound. All these spectral data, including IR, NMR, and absorption and PL, strongly supported the defect-free formation of the helical LADA structure. And to obtain the more evidence of the helical structure of this achiral monomer-based LADA polymer, so we tried the direct resolution of this polymer by chiral HPLC. So as I mentioned before, so this polymer or chiral element, so if the eluted fractions show optical activity, so we can state that this polymer has a chiral secondary structure. So until now, several examples of racemic helical polymer have been reported, but they are still quite rare. So after testing the series of chiral column using different elements, so we found a good condition using chiral package as a stepwise elution mode, where we change the solvent polarity during the separation. And the eluted component were then fractionated into 10 fractions, as shown here, and we emit the spectrum. To our delight, the former 7 and later 3 fractions showed this kind of the mirror image CD signal in the pi conjugated polymer backbone region. Or we can say that we succeeded in the synthesis of the optically active helical LADA polymer without any chiral element. And based on the TD DFT calculation, so we at the former fraction contain the P-rich helix and the later fraction contain the M-rich helix. And the key importance is that the disymmetry factor that for the fraction 1 is more than 10 to the power minus 2. So because the G value of the typical pi conjugated one-handed helical polymer, the order of 10 to the power minus 3. So this means that the helical sense of this fraction 1 would be sufficiently high. Next, so we investigate the thermal stability of this macromolecular helicity, and the CD intensity of this component showed almost no change in the tetrachloroethane even after heating at 50 degrees for 1 day. So this indicates the high stability of this helicity. But at high temperature, at 80 degrees, the CD intensity gradually decreases with time due to the helix inversion, and that is racinization. And unexpected decrease was stopped after heating at 80 degrees for 1 day, and intensity remained unchanged for several days, but gradually decreased again at 100 degrees. So the observed unusual temperature-dependent stepwise racinization is probably attributed to the molar mass dependence of the inversion barrier. So the low molar mass component would have a low inversion, more easily racemized than the high molar mass component. So to confirm this hypothesis, so we performed the same chiral HPLC experiment using the low molar mass polymer with value of the less than 7,000. So in this case, the all fractions show the no CD. So this is most likely because the low molar mass polymer chain cannot be isolated as a stable helical structure, low helix inversion barrier in solution as we expected. Here's a MD simulation of this left-handed 4-1 helical rubber polymer in fluoroform at 8. And this is the time-dependent change in the dihedral angle of the 4 adjacent fluorescent units in each single-termed helix. And this shows that the dihedral angle almost always have the negative, indicating that each termed helix maintains the left-handed helicity during the simulation at 50 degrees. So with 4 helical turn is the sufficient this condition that is consistent with the experimental data. And this MD simulation clarified that the helical pitch is about 1.5 nanometer, but fluctuate in the range of about along with unique spring-like extension and contraction motion. So, okay, so I'll summarize my talk. So we can now realize the precise control of polymer geometry, the structural designability of rubber polymer with quantitative rubber formation. Some of the polymers show the specific functionality, and we now believe that this polarization approach will realize the advanced functionality in the near future. Okay, so finally, so I'd like to thank the financial support from JSPS and JST Sakigaki, and also thank Professor Swagger and Professor Yashima, as well as the current and former staff and students who contribute to this research. And especially Dr. Hijikata has a great help for the MD simulation, and Dr. Wei Chen powerfully developed this helical rudder research field with us. And okay, so thank you for your kind attention. Yes.
Thank you very much, Professor Ikai, for the excellent talk. And so to the audience, please write your questions again in the chat. And so I will read the questions from the chat. And first question from Sankarao. Why did you choose those solvents only for solvent dependence? I think this was about the second topic, ABC and structure.
Okay, thank you for the question. So I think so this question is about this slide. So yeah, so I just chose this solvent, but I think so measure also the other we measure this CD spectrum in the other solvent, but yeah, totally almost no change. So this is due to the very rigid conformation of this chiral rubber polymers. So not so big meaning of the choice of the solvent.
Thank you. So the second question is from Dr. Soichiro. And how do differences from monomers affect the photophysical properties of the polymer?
Okay, so I think so. So I think so. This is I think good comparison of the monomer or the model molecule, small molecule, and the polymers. So I think so we can see. I think that the UV spectrum is very similar. So the wavelength is also the almost same. So I think so. For our other polymer, pi conjugation length is not so elongated compared with the model molecules. I think this is because our polymer is a phenocene type, not asyn type rather. So yeah, so our polymer is the optical property is very similar with model molecules, small molecules. Is it okay?
Thank you. So if you had additional questions, please write in the chat. So the third question from Feng-Kun Chen, and is there any chirality transfer or amplification more to the polymers? Why it seems that the intensity of the chiroptical properties of the latter polymers are not so strong? Thanks.
Yeah, thank you very much. Good question. Yeah, I'm very interested in the amplification of the chirality from the monomer to the polymer. Yeah, so so now I have this result of the chiral amplification. Yeah. So in the future, so I'm try so this field. Thank you very much for the suggestion. Yeah.
Thank you. Question is from Funju Yen. And thanks, Professor Ikai, for sharing these fantastic and beautiful works. From the results of chiral HPLC trace for poly 8Me under stepwise elution, does F10 close to the models?
Sorry.
If the so if the
F10?
fraction 10 close to the model compound, I think. So if in the retention time, I assume that the retention time of fraction 10 is close to the retention time of model compound. Or?
Model compound. Fraction 10. So I did the HPLC of the model compound, but I think the model compound eluted faster than the polymer. So the interaction site is very few. So I think so. The model compound the F10 the retention time is, I think, very different.
Thank you. So please ask one question as we still have some time. So it's quite interesting that the helical pitch is on the maybe temperature, so it's kind of fluctuating. And do you think there can be dependence of the optical electronic properties on this fluctuation? For example, if you frozen it or solidify it, there can be pipeline interaction between the helixes and the different layers, or if so even if the absorption is similar, what about the fluorescence quantum yield?
Yeah. Thank you very much for this is a very good point. So I'm in the spring-like motion of this other polymer, and we know this polymer show that totally almost no temperature show the temperature independent absorption and absorption spectrum. So but I think so. Yeah, I think maybe we need to study the spring-like motion of this other polymer. I think maybe this is very related to the optical property, and this spring-like motion is, I think, depending on the temperature. In the future. So I will try to clarify the relationship of the spring-like motion and the optical property on the other property. Thank you very much for your question.
So there's one clarification from Kunju Yen. So yes, I was wondering, is that the model compounds, so about this retention fractions. And so my main question is that increasing the degree of polymerization, G-abs will also increase.
Yes. Yeah. So I think so. We don't check so the molar mass dependence of the G value in this study, but we checked in the other study. Yeah. So the G value increase with increasing the molar mass. Basically. Yeah. So usually the rather polymers show the higher G value of the model compound. I think that about 2 or 3 times higher than the model molecules, typically.
So thank you so much for the clarification, really motivated works. So for the sake of time, last question from Mondu Maji is, I have one query about the 6-endo and 5-exo cyclization of alkyne. All of substitutions are 1. Any detailed comment on this will be highly appreciated.
Sorry, so this question is
so about the endo and 5-exo cyclization. I think that, so there was R1 as substituent, and I think about the selectivity of the cyclization.
So this related. So this question is related with the side.
I assume that this is about that dimethyl substitution that you. I'm not too sure about the R1 in this case. What's
R1? So I can't catch the question, the meaning of the question.
I'm. Okay.
R1.
It might be also about the isomers, because I think you didn't show the 5-membered ring formation in this case.
But 5-member. So we, yes, this our reaction. So we didn't produce a 5-member ring, just 6-member rings or the 7-member rings.
So he meant slide 25 is perfect. Here substitution is R.
Yeah.
Yeah.
So this methyl substituent increase the chemoselectivity, and so this is because this methyl substituent stabilized this, I think, the vinyl cation. So this active species. So this stabilization of this vinyl cation is I think the key point of the increase of the chemoselectivity.
And I assume that this acid-mediated catalyzed cyclization was previously optimized to give only 6-membered ring, right? So without the formation of 5-membered ring as byproduct.
Yes.
Yes, that was the question. But in this case, it was not due to the substituent, but the reaction condition to secure the 6-membered ring formation. Okay, so yeah, so Professor Ikai, thank you very much again for talk and for participating in this web seminar.
Thank you very much.
So, okay, so let us move to the last speaker, Professor Chunyan. And Professor Chi, if you could start sharing the screen, I will meanwhile introduce your background. So Professor Chunyan received her PhD from Max Planck Institute for Polymer Research. So this is in Mainz, working in the group of Professor Gerhard Wegner. Afterwards, she conducted her postdoctoral stay in the group of Professor Guillermo Bazan at the University of California, Santa Barbara. In 2007, she became a PI as an independent research fellow in the Department of Chemistry at the National University of Singapore, NUS, where she became later assistant professor, and she is associate professor since 2017. So her research interests include the synthesis of extended pi electron systems with novel structures, aromaticity, organic diradicals, dyes, liquid crystals, and functional mechanic electronics. And she is really making unique and impressive structures always. And she has received the Asian Core Program Lectureship Awards from Japan, China, Taiwan, Hong Kong, and South Korea in different years, and also received Young Chemist Award from the Department of Chemistry at NUS in 2016. And so she also got the Distinguished Research Fees Award from the Chemical Society of Japan and Distinguished Woman Chemist Award here. And she's an associate editor of Organic Characters from last month, if I checked correctly, and also serving in advisory board of many renowned journals, including Journal of Material Chemistry, C, and Chemistry European Journal. So the hard title today is Molecular Carbons with different shapes and sizes. So Professor Chi, if you are ready, please start your presentation.
Okay, good morning, everyone. So first, I would like to thank Professor Narita for the kind introduction and also for invitation. Today is great pleasure for me to share my work. The title of my talk is Molecular Carbons with Different Shapes and Sizes. When I start my independent work, so we first focus on acid-based molecules and materials. From acid building block, we made N-type acids by attaching electron withdrawing groups, and such molecules, they have a low LUMO energy level and can be used as a N-type semiconductors for organic electronics. We also develop acid chemistry and such as this molecule. Okay, it's longer than pentacene. If we benzene ring by sulfur ring, we can get the non-classical acids. In these type of structures, all rings have a dimension, so they are actually highly reactive. Since larger acids, they are not so just now, like Professor Bunz mentioned. So then we have to stabilize acid-based molecules. The approach developed in my group is to fuse 5 membranes on the zigzag edge of acids and to make a cyclopentyl fused acids and acid dimers. And they have improved stability, and some of them have been studied for links. Another approach is to introduce heteroatoms on the parallel position of middle phenol ring, and to make these structures, actually the central part is a quinodal unit. So just now mentioned to introduce the heteroatoms on the acid framework, and he made a lot of beautiful molecules, make a lot of other acids. And for our molecules, because the central part actually nodal unit, so we call them heterocyclic dimensions. And these type structures, they also have improved stability compared to the corresponding acids. Then later we move to 2-dimensional peri-acids, nanographene edges, and then further to 3-dimensional carbon nanobelts and curved nanographene. And of course, we are also interested in other pi structures like macrocycles helicins and non-alternate hydrocarbons. Some examples to introduce. The first type structures I will introduce the heterocyclic dimensions. As I mentioned, actually we introduced sulfur atoms and oxygen atoms framework. Then we made sulfur and oxygen heterocyclic dimensions. When the central conodal unit is long, then molecules show open shell diradical ground state and with a central unit. And when these molecules include 5 membranes like this one and this one, okay, they also have a dipolar character. And if the central conodal unit is long, then this molecule, it has both diradical character and dipolar character. So here I just use one slide to summarize this work. Then go to the next type of structures, non-alternate hydrocarbons. That means these molecules include 5 or and 7 membranes. For example, these are co-expanded pentalenes, and these are fused and they include 2 anti-aromatic indocin moieties. And these are azulene fused acins, have aromatic azulene units and aromatic acin units. The last type of structure, and they are azulene fused acin indocins. They include aromatic azulene units and anti-aromatic acin indocin moieties. So these systems are very important to understand how the interactions between it influence the electronic properties of the whole structures. So here I just take 2 examples to introduce. Pentalene is anti-aromatic, is highly reactive. So many chemical modifications have been. For example, one approach is to fuse benzyl nitrogens at the periphery of pentalene and to make a dibenzyl pentalene. And this type of structures have improved stability, and some molecules have been studied for. Another approach is to insert benzyl nitrogen or acin unit between 2 5 membranes and to make this type of structures. However, they are reactive. For example, when one benzyl nitrogen between 2 5 membranes, so this molecule is called S-indocin. It has closed shell ground state. And the parent S-indocin was reported by Professor Hafner in 1963. It's sensitive to oxygen and trace amount. This molecule has one isomer. It's called AS-indocin. The successful synthesis of AS-indocin has not been reported. In 1986, Professor Hafner reported tetrabutylene, and based on X-ray analysis, this molecule has highly delocalized D2H structure. After 1986, successful synthesis of further expanded pentalenes has not for over 30 years. This mainly because people thought this kind of structures are not stable, but it's great interest for us to understand the electronic property, electronic structure of this type of molecules and why they are not stable. So then we try to insert a naphthalene unit between 2 5 membranes. And for this structure, actually, we can draw a central naphthoquinone dimension unit. It has one for both molecules. Actually, we can draw open shell diradical resonance structures. Now the question is whether they have open shell diradical ground state or not. Then based on this consideration, we made these 2 molecules with all blocked by Barkey groups of phenolens. Then based on the theoretical calculations and experimental results, we find both molecules, they have open shell diradical ground state. The diradical is around 30%, the diradical character of 2 is around 48%. So just now we know that for indocene, it has closed shell ground state. We just insert one more benzene ring, then both molecules now, they have open shell, diradical ground state. Small change in the structure of anti-aromatic system can cause large difference in the ground state. So now we know why they are not stable, because they are anti-aromatic and they also have open shell, diradical ground state. So the crystal structures for molecule 1, based on X-ray analysis, it has a bond delocalized D2H structure, and for molecule 2, it has bond localized C2H structure. Both molecules, compared to molecule 1, molecule 2 has larger ICS values, small HOMA values in each ring, and also larger bond length alternation along the periphery. So molecule 2 actually is more So we know that for S-indocene is anti-aromatic. Then how about if we fuse two S-indocene units together to form fused S-indocene dimers? In this case, we can draw two valence tautomers. A, it has 22 pi aniline-like conjugation pathway along the periphery. And for structure B, it can be considered as two fused S-indocene moieties which share. Actually, fused dimers with two anti-aromatic units are very rare. When I search literatures, I only found one example is a fused pentylene dimer. So these molecules were reported by Professor Hafner. And this type of structures, they have a weak aromatic character. Then for fused S-indocene dimers, we can draw two open shell resonance structures. Similarly, for AS-indocene, we fuse two units together, then we can also draw two valence tautomers, and also two open shell diradical resonance structures. Now, many questions come. How about stability of this kind of structure? Then are they anti-aromatic or aromatic? Okay, now how about their ground state? Then we designed and synthesized two molecules, and this one is a fused S-indocene dimer. We prepared the key intermediate diketone compound, the nucleophilic addition of 4 with 2,6-dichlorophenol magnesium chloride to give a diol intermediate 5. Then 5 is converted to the dihydral compound 6 in borotrifluoride and triacylcysteine compound. Then 6 was treated with potassium terdibutoxide to give a dianion, then followed by oxidation with p-chloronyl to give a target structure. We also made the fused AS-indocene dimer. It can be synthesized in a similar approach. Then for both molecules, again, they have open shell diradical ground state. The diradical character of fused AS is around 64%, and the diradical character of fused AS-indocene dimer is around 67%. So both molecules actually they have a small singlet to triplet gap. And these are single crystal structures. As you can see, the all reactive sites are blocked by phenol rings and dichlorophenol groups. Actually, we also did a lot of experimental measurements and combined with theoretical calculation. Then we can conclude that for the fused S-indocene dimer, it has localized anti-aromaticity on each S-indocene unit. Then for fused AS-indocene dimer, it has 22 pi electrons along the periphery. So this molecule actually has weak global aromaticity. Then the next part is about nanographene with a zigzag edge. The typical nanographene with a zigzag edge they contain several rows of SM moieties which are polarly fused together. These type of structures, they have a large diradical character, so they are highly reactive. So then we must stabilize these curves by attaching Farki groups and electron withdrawing groups. We can also fuse 5 membranes on the base position of periacenes and to make new pi structures, and they also have improved stability. Of course, benzene rings on the base position or on the zigzag edges of periacenes and to make new pi structures with better stability, and at the same time, they still keep the open shell theoretical ground state. So here I asked to introduce. So before 2020, only few isolated periacenes were reported and synthesized by wet chemistry. For example, these are teransen and quarteransen reported by Professor Kuber's group. These are peritetracenes reported by Professor Wu and Professor Feng's group, respectively. The peritetracenes have theoretical character around 52% to 72%, and 3 hours to 7 hours under ambient conditions. This depends on the different substituents. Then in 2021, Feng's group reported this periheptacene, and this molecule has theoretical character, and this molecule actually is in situ generated. Okay, it cannot be isolated, and the half-life time is around 25 minutes under inert conditions. In 2021, we made this molecule 3-periacene. It contains 3 rows of tetracene moieties, which are poorly fused together. This molecule has theoretical character around 95%, so it's much higher than that of peritetracene. This molecule is much more stable than peritetracene. The half-life time is around 157 hours under ambient conditions. The better stability of this molecule is due to attachment of bulky groups at the zigzag edges. One group is methyl group, like group. So they somehow have donor receptor interaction. So that means they have a factor which can stabilize the radical species. Another example is this one, perihexacene. This molecule has theoretical character around 91%. The successful synthesis has not been reported. Our particular interest is to fuse 2 benzene rings at the base position and to make this new pi structure. The core of this molecule actually is pentacene. So then we called it Then many questions come. How about the stability and ground state of this molecule? Is aromatic or not? Then we searched literature, we found 3 reported circumenthenes. The first one is the circumbenzene. We also called it reported by Shaw in 1932. The second one is a circumnaphthalene. It's also called orally, reported by Clark in 1948. The third one is the circumanthraceene, reported by Diderot in 1991 and Feng in 2018. Compared to the corresponding periacenes, all of these circumanthenes, they have improved stability, and they all are closed shared compounds. Now we know that for peritetracene, it has theoretical character over 50%. But after fusion to benzene rings, this molecule now has closed shell ground state. So that means from to the corresponding circumenthenes, then the theoretical character is reduced. Now, how about the theoretical character of circumpentacene? Then we did calculation. We found that the circumpentacene has theoretical character around 40%. So then we did resonance structures, and this is the theoretical resonance structure. In this structure, we can draw 7 aromatic 6 rings. And this is the spin distribution map. The spins are mainly delocalized along the zigzag edges. And this is the synthetic route for circumpentacene. So we made this key intermediate, the helicene with OTF group. The OTF group is first converted to the B-pin, and then molecule 3 reactivates 4 by action to give a 5. Then 5 reactivates alkyl chloride to give a diiodide 6. Then 6 is treated with DDQ and triplet acid, and to give a fused diiodide 7. 7 reacts with lithium by lithium halogen reaction and followed by nucleophilic reaction with 2,4,6 trichlorobenzaldehyde to give a diol intermediate. Then which underwent the Friedel-Crafts reaction to give a dihydral compound 8. Then 8 react with potassium toluene to give a dianion, then followed by oxidation with p-chloronyl to give a target structure. Second shows long wavelength absorption band with a maximum at 906 nanometer. We also did a photostability test under ambient air and light conditions. So the half-life time is around 70 days when monitored at 6 nanometer. So that means this molecule actually is very stable. And this is the cycle automatic curve. We can observe 2 reversible oxidation waves and 2 reversible reduction waves. So that means this molecule can be oxidized state and reduced to the dianionic state. So this is the single crystal structure. The backbone actually is slightly distorted due to attachment of bulky groups. Then based on X-ray analysis, the bond B, C, D at the 4 corners, they have a double bond character. And the bonds E and F, they have a single bond character. It's due to elongation induced by steric repulsion between. And the HOMA values listed in each ring. The ring highlighted in green color, they have a largest HOMA values. The rings in white color, they have a much smaller HOMA values. And the rings, they have HOMA values between 0.63 to 0.75. So that means for neutral molecule, it has a dominant local aromatic character. Then we also measure the VTE, and this molecule indeed show open shell theoretical ground state. The singlet to triplet gap is around -4.47 kcal per mole, so it's similar to that for calculated data. And to further understand the electronic structures and aromaticity of neutral molecule and charged species, we also did calculations on NRCH values and 2D RCS map and ACID plots. For example, for neutral molecule, the rings highlight color, they have a very small negative RCH values. That means these rings, they are non-aromatic. So the electronic structure of neutral compound can be regarded as a dibenzyl circum with a 4 K-region double bonds. The 2D RCSS map and ACID plots show a similar result. Then for dication, the rings C, D, P, Q, they have a small positive RCH values. They are non-aromatic. The ring H also has a small positive RCH value, but it's different. Because this ring is surrounded by 6 phenolins, so it shows small positive RCH values is due to ring. Okay, so then the electronic structure of dication can be regarded as a benzene fused chlorine dimer and with 2 positive charges delocalized along the 2 zigzag edges. And 2D RCSS map and ACID plot also a similar result. Then for dianion, actually it shows a similar electronic structure to the dication. Then the last part is about 3D pi structures. Here I also give you some examples. So these are curved and these are 3D carbon nanobells. And this one is a microcycles in a microcycle superstructure. And this superstructure actually shows magnochromic and thermochromic behavior. And these are cage cells. So today I will mainly talk about 3D carbon nanobells. Before 2020, only few fully conjugated carbon nanobells were reported. For example, this one is a segment of nanotube reported by Professor Thieme and Professor Sigawa in 2017. And this one is a chiral carbon nanobelt reported by Professor Miao in 2018. 18. And this one is a finite nanotube, the ESOBI in 2019. Many research groups tried to synthesize the zigzag carbon nanowells, but they all failed to give target structures. This is because the zigzag carbon nanowells are deltative. The cyclosines, actually, they have a high reactivity along the zigzag edge. They also have a high strain. So usually, the hydrogenated molecules and addition products were obtained. In 2020, we designed this molecule, octobenzyl 12-cyclosine, and we successfully prepared this compound. It's a segment of 12-0 carbon nanotube. In 2020, Professor Thieme and Mikawa also reported this zigzag carbon nanobelt is dodecobenzene 18-cyclosine. The structure is confirmed by a single crystal. In 2021, then Professor Miao reported these two carbon nanobelts like arrangement of Haskins in the unrolled lattice of the 16-0 and 24-0 single-wall carbon nanotubes. Now, how to synthesize our octobenzyl 12-cyclosine? So we started from molecule 2. Molecule 2 is tetrabromide. It can react with lithium to form dibenzene. Then react with by DSR direction, we can get synsarsamol 3 and transarsamol 4. The synsarsamol 3 actually has a C-shaped conformation. It can also react with lithium to form dibenzene. Then react with 1 by DSR direction, you can get tetroepoxy nanobelt 5. Then treatment of 5 with titanium tetrachloride and lithium, we can get the target structure. So here we attach to the butyrphenolens. Without to the butyrphenolens, we cannot get a target compound. We only can get hydrogenated products. And this is the single crystal structure. So as you can see, all zigzag edges are blocked. And the attached phenolens, they are almost perpendicular to the molecular backbone. And it shows cylinder-like conformation and is fully conjugated and rigid. The periones are by the belt. So this molecule actually has a high strain. So this is the reason why the reaction yield is low. The diameter of this molecule is about 9.2 angstrom. And this is the 3D packing structure. It shows 1D trans interactions. Then after this work, we tried to do calculation. So we did calculations on these molecules with 5 membranes, and then we compared to the molecules with all 6 membranes. We found that the structures with 5 membranes, they have a smaller homolumo gap. So that means the structures with 5 membranes, they are more conjugated. So then we plan to make containing both 5 and 6 membranes. Then with such literatures, we found that Professor Schutter tried to synthesize this kind of carbon nanobelt almost 20 years ago. However, he could not get a target compounds 30 and 31 with the oxygen bridges. This mainly because the target structure has very large strain. Then we analyze the strain, and also we propose new synthetic rules and think about the students, and finally we prepared the 2 non-alternate carbon nanobelts. So this is the single crystal structure of one of molecules. So it also shows cylinder-like conformation, so it's fully conjugated. The diameter is between 12 to 13 angstrom, and this is the first carbon nanobelt which emits a strong red fluorescence. The fluorescence quantum yield is around 34% and 56% for 2. And interestingly, this molecule can be oxidized to the dicationic state. Dication shows open shell diradical ground state. And this is the GMIC image. It shows clockwise recurrent delocalized along the top edge and bottom edge. So that means the dication is global aromatic. So now I give a summary for my talk. So today I introduce some soluble nanostructures. I introduce their synthesis, stability, aromaticity, ground state, and electronic structures. So for the next step, we will study their applications for electronic devices, spintronic devices, and so okay, finally, I would like to thank my group members. So this photo shows my current group members and also my current group members, and also the former group members, and also thank my collaborators and financial support, and thank you for your attention.
Thank you very much for the wonderful talk, a lot of impressive molecules. And so now accept questions. And so the first question from Dr. Soichiro Nakatsuka: how does aromaticity and anti-aromaticity affect that reactivity? For example, reaction rate of electron-related reactions or lifetime of photoexcited state.
So usually we say if a molecules they have an anti-aromatic character, they are reactive. I mean, compared to the aromatic compounds, the anti-aromatic compounds usually have a low stability. Yeah. So then for reaction rate of de-aromatization reaction, we didn't try. Yeah. So because anti-aromatic system, we always think about how to stabilize such structures. So usually we attach bulky groups and something, then we can still make stable anti-aromatic systems. Then we can do catalyzation. Yeah, we never study aromatization reaction. The lifetime of a photoexcited state. The lifetime of photoexcited state we didn't compare for the aromatic system and the anti-aromatic system. So now I cannot give you. So I think it's interesting part to study that. Yeah.
Thank you. So there's another question about the stability, and so why these acids are less stable and how to make ultra stable. So maybe I think you explained, but maybe you could give some basic introduction.
So sorry, which question?
So this is about the stability. So I think it was not too. So I think you could explain why these are very unstable and how to make them stable. I know you had one slide, and maybe you could show it again and briefly give some more explanation.
Okay. So maybe I take, okay, so for first two systems, yes. How to change my slides. Okay, so take this one as example. Okay. So then I talk this system first, then later I talk about the nanographene. So for this type of structures, as I mentioned, so actually nobody prepared this type of structure in many years. This is because people think they are not stable. Yes, they are very reactive. So then so we first do calculation. So we find the terminal groups, the terminal positions in the fifth membrane, they are highly reactive. Then we think about to block the reactive position, central part. So then even we blocked all reactive positions, actually these molecules, you know, we can get a single crystals, we can do a lot of characterizations, but they are not stable. So my students run columns, my students do all characterizations in the inert conditions. It's very difficult to prepare these two molecules. But it actually is already very, very important actually with single crystals. Then for this system, I mentioned again, for periacenes, they are not stable. Then for this molecule, actually, so you see we we found a very special strategy when we compare the peritagosines. So this one is smaller, has a smaller diuretical character, but for 3 periacenes, the diuretical character is much larger. But this one is more stable. So because here we attach one electron, another one is electron withdrawing group. They are very close to each other. And then the diradical spin actually is mainly delocalized along these three carbon atoms. So then here, the donor accepting interaction between AR1 and this like have a charge transfer character, and we found that they can stabilize the radical species very efficiently. And later, actually, when we prepare circumpentascenes, we always use this strategy. So for example, in this molecule, so one R group. So here, because I didn't mention, okay, maybe go to the next slide. Okay, so you see, methyl group, electrodonating group, and the AR actually is trichlorophenoline, is electron withdrawing group. Then when we design this molecule, I mean, by this strategy, so as you see, this molecule is very stable. So the half-life time is around 70 days. Then we go back to okay, so this is the one strategy, donor can stabilize the radicals. So another approach, I mean, when we fuse 5 membranes and 6 membranes at the base position, we can get new structures. In this case, actually, the electronic structure is changed, and they also have a better stability since. Of course, for the last one, when we fuse benzene at the zigzag edge, of course, it has improved stability. Yeah. I hope I answered this question.
I believe, thank you very much. Okay.
Yeah,
very nice explanation for the audience. So another question from Mundu Mazi is fantastic talk, enjoyed throughout. I have one general question on nanobelt. Except single crystal X-ray, are there other ways to characterize such exotic molecules?
Okay, so this depends actually for our first carbon nanobelt, because you see the reaction yield is very low because the molecule has very large. In that case, we get a single crystal. We also measure MR, proton MR spectrum, and also UV absorption spectrum and the cyclovoltammetry curve also for the first one. Yeah, but for the second one, we can do more characterizations because higher, and also so for the second molecule, because it shows reversible oxidation, and we also can oxidize the neutral compound to get a dication. And for dication, also for the neutral compound, I mean, we check them and for UV absorption spectrum and fluorescence spectrum, and also cyclovoltammetry. For dication, we also measure ESR spectrum, so we can observe the ESR intensity increase with temperature. So it is shows radical ground state. Yeah, but for diradical is too reactive, then we cannot get a single crystal. So then other things, yeah, like absorption spectrum for dication, we also obtain the spectrum. Yeah.
Question is from Professor Ikai. Thank you for your amazing talk. I have questions about the carbon nanobelt. That's the carbon nanobelt in the last topic have an ability to encapsulate in the cavity. Another one is it possible to connect the carbon nanobelts through non-covalent interaction like long tubes?
Okay, very good questions. So for first one, carbon nanobelt in the last I have an ability to encapsulate the gas molecules in the cavity. Actually, I asked my students to try to host some gas molecules. We try to put a C60, but actually they do not form a complex. So tell you another information because I didn't show the packing structure. So for in the solid state, actually maybe I go to structure. So our molecules, they have a trifluoromethyl, this one. Yes, trifluoromethylphenolene. The trifluoromethyl group actually insert to the cavity of a next molecule. Okay, so that it serves the guest by the molecule itself. Yeah. Then the second question is possible to connect carbon nanowells through no covalent interactions to make long tubes. Now for both these two nanowells is difficult because to stabilize these two nanowells, you see we attach a lot of Brachii groups on the zigzag edge. So then in this case, they cannot. Yeah, for first one in the solid state packing is channel 1D channels, okay, through carbon hydrogen pi and van der Waals interactions. But I think the distance is still larger. Okay, then for the second one, we didn't observe the channel in the packing structure.
Yeah, so thank you very much. So are there any questions? If you could write in the chat, I think we can have one more question. Okay, so but let me ask one question. So the Sakan pentosine, so that one is the directly character is like 40%, but it's direct. So at room temperature, you don't see any NMR signal and only the EPL signal.
At the room temperature, I think I cannot remember exactly. I think 40% usually at the room temperature we can observe peaks.
And if have you checked at the lower temperature you can
yes,
kind of
for all direct noise, actually we conduct the VT-MR spectrum. Yeah, for example, but I cannot remember exactly because we made so many noise. Yeah, so for if some molecules they have a very large direct character, they may show broad peaks or maybe no peaks at the room temperature. In that case, we need a reduced temperature. Decrease the temperature, then we can observe the sharp MRP. Yeah, but for the direct character maybe is a small. Yeah, then in that case, maybe at the room temperature is still show sharp peaks. Then we need the increased temperature, then peaks will become broad. Yeah, and maybe disappear. Yeah, depends on the direct character.
Have you observed that you see both NMR and EPR at the same temperature from the same sample? Or...
Yes. You mean so yeah, so for most of direct noise we study VT-MR and VT, they are very consistent. For example, if a molecule has a small direct character, then at the room temperature, maybe the peak just slightly broadened. Then ESR intensity is weak. Temperature, then the MR peaks become broad, and then ESR intensity increase.
Yeah, I see.
Then
so
yeah, so similarly, then when the molecules have a large direct character, maybe at the room temperature, the MR peak is already broad, and the density at the room temperature is also already very high. Yeah,
I see. Thank you very much. So I think it's time to wrap up. So thank you very much again for the excellent talk.
Yeah, thank you for the invitation. Yeah.
Explanation in this Q&A section. So, Charlie, do you like to close?
Yeah, thank you very much, Professor Narita. So firstly, thank you very much to you
can I first then give the closing remark, and then I will first wrap up from my side and give it back to you. So I'd like to thank all the speakers again. So it was wonderful to have 3 of you here. And I think Uwe needed to thank you very much again for the really wonderful and excellent talks, a lot of impressive results. I also learned, enjoyed a lot. And thank you for all the audience to joining. And yeah, if you are interested, please let me know. And we are actually a focus issue, solidography in nanoarchitectures. So yeah, I was very honored, happy to chair and give it back the stage back to Charlie.
Thank you very much. So from my side, I'd like to take a big thank you to you for chairing and so well today. I really appreciate that. For our wonderful speakers who have given such interesting talks today, thank you for sparing the time to talk to everybody. Thank you to the Cassini platform for ensuring this has been a smooth and for Fadwa as well, who has been helping to monitor the comments and questions as they come in. As Professor Narita said, if you have any questions about the journals, either organic materials or sustainability now, please feel free to reach out to us. There is further information on the website and we would love to receive your submissions. So with that, I'd like to close the session for today, and the recording will be available shortly afterwards in the coming days. So thank you very much. Take care.